All right, class, quiet now, pay attention, stop throwing paper darts, quiet in the back. Very, very important. We must understand this, because if we don't understand this, then we are likely to get sucked in by charlatans who want to tell us that gravity is not a real thing and say things like it's not a force and yeah, all sorts of crazy stuff like that. So I need to arm you, boys and girls, by way of being fair to you, with the information you require to be able to make a sensible argument against such ass-hattery, really. All right, so today, what are we going to do? Well, we're going to play with corns. Yes, we are. That'll be fun, won't it? Absolutely a ball, I'm sure. So I need to make some caveat statements here before we get going so that you can understand what it is I am doing, hopefully, here. Right. Let me explain to you what I'm doing in simple terms. I'm using a two-dimensional representation of a concept which is used successfully to predict the behavior of two bodies in space. Okay. All actual numbers on here are arbitrary. The actual numbers in the reality, the objective reality in which we find ourselves is already determined. They are values that have been measured by physicists and put in place, so we understand what they are. This is a schematic. Okay, this is a back of the envelope sketch for you if you like to think of it that way. All right, what are we looking at here? We are looking at a two-dimensional representation of a three-dimensional cone in space with a lovely blue line on it, which happens to be a thingy called a geodesic. A geodesic, yes. Now, obviously, we can spin this thing around and look at it from any angle you like. It makes no difference to anything, really, because everything on it is all relative to everything else on it. And we can move it around and look at it from different angles, and we can turn it this way and that way, and, pretty much any old way you like. Geez, isn't it fun playing with cones? Anyway, let's do some actual learning. So let me just get this cone situated where it was at the beginning, just because I'm a little bit autistic and, just can't cope with change. All right. There we go. Right, so here we have a cone with a geodesic drawn on it. For those that don't know, what is a geodesic? A geodesic is a straight line on a flattened three-dimensional surface. So in the case of a cone, you'd split the cone at any one given point. Let's say on the exact far face of the cone in a vertical line straight through the apex of the cone, directly through the base of the cone at an orthogonal angle. You'd split it there for fun, and you would open that cone out, and it would splay out as to look more like a portion of a circle, because that's what a cone is when you flatten it out. And hey presto, the curvy line that we see here on this three-dimensional surface, the geodesic, becomes dead straight. It's a straight line. Okay, brilliant. So there you go. There's gravity explained for you pretty much in a nutshell. Hope you enjoyed the lesson. Join me next week when I'll confuse you even more. No, seriously, I'll probably fill it in a bit more today, shall I? All right. Well, what is this cone a representation of? Well, it's a two-dimensional representation of a four-dimensional structure. What is the four-dimensional structure? Well, the four-dimensional structure I refer to is the three dimensions of space as we see them to be, X, Y, and Z. And the fourth dimension is that of time. Yes, old wibbly-wobbly, timey-wimey stuff, as Doctor Who would say. All right, so what I would like you to do in order to understand what gravity is and why it occurs is this. take that vertical line that you drew down the exactly opposing face of this cone and draw it now instead down the front face of the cone so that it intersects this geodesic into two equal parts. That bit of the line which drops away and gets lower to the left of our new line, and that bit which is on the right of it, which also drops away. So imagine yourself to be currently at the highest point on that geodesic arc on this two-dimensional drawing. Okay. Now, does the height up the cone represent your height? Yes, it does. It's a representation of your height above any surface, any hard surface that would prevent you from moving through that surface because of the mutual repulsion of the electrons in your body with the electrons in its body, i.e. a thing that would stop you from accelerating towards the center of mass, or the other object accelerating towards you, as is equally true when you consider relativity and the sum F equals ma, which holds true. Newton was brilliant, an absolute genius. Newton said many things that were absolutely correct, and that was one of them. F equals ma, pretty much. Excellent, good. So, right, let's imagine you are stood at the blue line at a given height above a given surface. Let's say that surface is the surface of the world upon which we live, that thing that we attribute gravity to. In actual fact, it has gravity, and so do you. When you fall to Earth, actually both objects are being attracted towards one another. It's just that because of F equals ma and all of that kind of bizzo that Newton came up with all those years ago. Well, he just described it, really. He didn't come up with it. He didn't invent it. Goodness. The thing that appears to be moving the most is because it's moving the most. The other thing is still moving. It's just moving infinitesimally because it has massive amounts of stuff where you don't have very much stuff comparative to the Earth. The Earth weighs a lot more than you. So anyway, that's that one. All right. So let's say the bottom of the blue line, the blue geodesic line as we see it there, it has a dimension. That has a thickness, this line. Let's say the bottom of it is your feet, and let's say the top of it is the top of your head, and you've just done what I suggested that you should do, Nathan Oakley, to prove that gravity is a thing in my video last week, and that is you've stepped off a platform at a given height above the surface of the Earth with nothing supporting you and no equipment to arrest your fall due to the actual thing, gravity, which will actually draw those two bodies together in space over the next very short period of time until you suddenly meet said surface where there is mutual attraction due to the much more powerful electromagnetic force, and that will halt your movement towards the center of mass of the Earth quite suddenly, Nathan, and then we'll all clean up and go, well, there you go, gravity is a thing, Nathan. That's what would happen. Look, I'll show it to you here. This is a thing not involving having to clean up so much afterwards. Here is my rubber representation of Venus from my very fine video the other day about how it is we know how far away the sun is. Check it out if you haven't seen it. It was great. I think anyway. Of course, I have to think that. Anyway, here is Venus. If I drop it, look at that. It falls. It accelerates towards the surface of the Earth in a straight down styly. Look, it did it again. And pretty much every time, Nathan, and actually it accelerates at a rate which is exactly predictable. So seems like gravity is a thing. So that's that one covered off. It seems like that would be a repeatable observation, which provides us with predictable results every time, a coconut, and twice on Sundays. Good. Okay, so we have gravity. Awesome. So now we just can stop arguing about whether it's a thing, and now we just need to understand why it occurs, and then we can also, once we've done that, we can stop arguing about whether it is a force or whether it is an effect, because actually that doesn't matter. You heard it here first. It's the whole line of logic is lacking, actually, in any form of logic. It doesn't matter. I'll explain that as we go along a bit more. Anywho, you're still on the blue line at the highest point. Why are you at the highest point? Well, let's just put you there. Why would we put you there? Okay, let's say we put you there because the vertical line which runs directly down, vertical as we look at it, because it will be sloping away from us on this view of the cone, that vertical line, as we see it in 2 dimensions, that represents this instant in time progressing as the cone inexorably rotates, probably in the exact opposite direction to what you see my finger rotating at this point, because my camera angle will be reversed. Anyway, it's clockwise in this example just for fun, although that actually doesn't matter in this example, and I'll show you why as well. It doesn't matter which way you're rotating it. You're rotating the cone. Okay. All parts of the cone rotate around the central axis, which would be the genuinely three-dimensionally vertical line through the apex of the cone through to the absolute center point of the circle inscribed by the base of the cone. It's rotating around that, shall we say. That is what time is. Time is progressing inexorably at a set rate. However, the rate at which time proceeds, as viewed from various vantage points, does not seem to be the same, because actually a horizontal ring circuit around the cone at different heights is a different distance in this 2-dimensional idea. So what this cone shows, or what it schematically demonstrates, is that at the base of the cone, down here, at the base of the cone, because that's a longer distance, doesn't represent a genuine distance, by the way. And I'll get to that in a minute. It represents a circumferential distance around this cone. Okay, nothing to do with 3 dimensions of space. Forget that. Anyway, a longer circumference around the base of the cone represents time moving more slowly past any given point on the base of the cone. Let's say in this 2-dimensional view, vertical line through the apex of the cone down to the base of the cone. It intersects the base of the cone at this point here. That point represents a point in space, any point in space. Okay, that point in space being the surface point, the surface on, let's say, the world, okay? That represents the surface of the Earth in a directly straight vector line between that point on the Earth and the center of mass of the Earth at that point. Okay, that was a bit of a mouthful, but that's what it is. Okay? That base of the cone represents a force that would prevent a body from moving through that surface, that solid surface. The repulsion of the electrons in the surface of the Earth to the electrons in the mass that makes up your body. Okay? So if you are at this instance in time, which is now, so let's get this angle sorted out so that we are actually, there we go. This is now, right here. You are stood, having stepped directly off the platform at a height designated as whatever that is, above the surface of the Earth, and you are progressing through time, which we are diagrammatically showing as being orthogonal to the distance above the surface of the Earth. Now, why did I say it's nothing to do with 3 dimensions? Well, here's what it is. This is a 2-dimensional representation of a 3-dimensional thing, a 4-dimensional thing, I should say. Time and 3 dimensions of space, X, Y, and Z. Okay. What we are showing on the vertical distance here is a vector distance from your body to the surface of the Earth in a direct line between you and the center of mass of the Earth. In whatever direction that is in actual space-time to any given external frame of reference, which is impossible to impose one of anyway. So this cone in real space, if there was such a thing, could be on that angle there, it could be on that angle there, it could be oriented like that, it could be, it doesn't matter. I'm showing it to you facing in the direction I am showing it facing to you, purely because it makes it easier, I think, for you to understand what is happening. Okay. Objects move through 4 dimensions. Those 4 dimensions being X, Y, Z of space, and T, time, which is a constant that progresses in a given direction, either left or right of the center of the vertical line that we were talking about before. Okay. Because this is a geodesic, it is the shortest world line that thing can move through those 4 dimensions in, the 3 of space and the 1 of time. Okay, if you have no time, then you have no movement. So that's one proof that space and time are indeed inextricably a 4-dimensional thing. Here's another one. If I said to you, I'll meet you at pub, what's the first question you're going to ask me? Great, pal. When? Okay. What about if I said to you, pal, I'll meet you at 6? What would you say? Fantastic, knob jockey. When? Where? God, get it right. Where? Right. Well, it's at pub. So you need 3 dimensions of space, and you also need 1 of time, so that you can actually meet. Events can meet in the space-time continuum. So we all move through space and time inexorably throughout our existences. Okay. Our movement through space and time is a thing that we call our world line. We have a world line, each of us, so does every other object in creation, including this Venus model that has a world line. It's being affected by me at the moment because I'm actually applying a force to it to force it to do something other than what it was doing before that, which was remaining at rest relative to me and relative to the Earth as a whole. However, not stationary in actual space if such a thing existed, because the Earth is spinning around and flying through space and going around the galaxy, and the galaxy's flying through the universe. It all adds up to well over a million kilometers an hour actually at complete rest. It's quite fascinating, really. But there you have it. Okay, so we're stood at the top of this line at this instant, which we call now. We are progressing through time. Let's move the cone in an anti-clockwise direction just for fun. Let's move it such that the cone itself rotates, which is the movement of time past the vertical line of this instant, and we'll see what happens to the geodesic, the straight line movement of the body, which has just stepped off the platform in that space time, and see what happens to it, shall we? What fun. Here we go. Oh, look. At first, you don't seem to get much closer to the Earth, but moving at the same rate, I'm not doing this at a steady rate, but near enough to a steady rate, what you'll see is because of the slope of the line, it gets quicker and quicker and quicker to the point where we get to about here. And that is a point, Nathan, where your squishy body hits the very, very hard surface of the concrete car park that I was suggesting you place underneath that platform to see if gravity is a real thing, and you splat. And that's when we all start looking for the spades and shovels to scoop up the remains, Nathan, and clean up. And we'll be looking for some hoses and things to clean up the car park to make it safe for consumption once more. Pretty much that is what gravity is. That is what causes two objects to come together in space over time, unless a force causes them to move off that geodesic line and remain where they were, pretty much like the platform, which acts as a force because it is a force because the matter in the platform has electrons which repel the electrons of your body strongly enough to prevent you from falling through that platform and following your geodesic line to its inexorable end. In exactly the same way that the surface of the Earth does when you're stood on the surface of the Earth. Aha! Yes, says some clever people. But what happens when you run time in a reverse direction? What would you then not be repelled away from the center of mass of the Earth, and the Earth would be repelled away from you with equal and opposite fortitude? Well, it seems like not actually, because actually if you take the vertical instant of right now and instead of progressing right nows in what we perceive to be the forward direction, you progress time in the backward direction with respect to the way we perceive it to be, what comes before the other thing, the chicken and the egg and all of that. Let's see what happens to you, Nathan, if you suddenly found yourself moving backwards in time, however, having been on a particular non-geodesic line, in other words, a vertical line around this particular schematic cone here, because of the force of a platform holding you there. Let's say the platform is nominally, well, I have to call it anti-removed, don't I? Because we're moving backwards in time. Anyway, the platform is not there, and it will be there. To think of it that way, but let's run time backwards and see if you actually get repelled away from the surface of the Earth. Oh no, look, what happens? Gravity still works exactly the same way when time runs in the other direction as well. So there's a pretty good argument, to back up what really is a semantic decision. Is gravity a force or is it an effect? I still think it can be perceived and conceived of as both equally, and why not? It doesn't matter. The only thing that matters is what we actually observe to be occurring. So pretty much you take two bodies which therefore have a given mass and you separate them by a given distance in any direction in three-dimensional space, the centers of mass of those two bodies, and those centers of mass will come together as a function of time, whether time runs forward or backward. So that's interesting, isn't it, for Big Bang people? I'll cover that another day. Anywho, they will be drawn together inexorably over time, accelerating more and more so until the surfaces of said bodies come into contact and they interact with each other by way of the electrons in that matter interacting with the electrons in the other matter. Pretty much. That's gravity. That's how it works. It is a force because force can only be measured and is defined, therefore, as the effect that it has on bodies. There is no other way to measure a force except via its effect on bodies. Does gravity affect bodies? Still yes. Every time, predictably. So, good. Something is acting upon that ball predictably every time I set that observation up and make that observation. Does it match what happened last time? Yes, it does. It's a force. It's a real thing. It's the very thing that holds a larger amount of gas molecules in a smaller area of space closer to the surface of the Earth than it does further away, and that pressure of gas gradually drops away over distance away from the surface of the Earth until such time as it becomes, to all intents and purposes, in equilibrium with the pressure of deep space, which, by the way, boys and girls, is not zero. It's 10 to the minus 17 torr. And so that's where the expansion of the gas stops. So, is there a container for the gas around the Earth? Yes and no. It is gravity, which is both an effect and therefore a force. So, yes, there is a container. It's not a physical thing, but it's a container nonetheless because the gas is contained in that area of space, pretty much, give or take. It's able to fluctuate around within a certain amount of altitude, but the physics dictates how much of that happens and the mixing of the layers and all this kind of stuff. There you go. There it is. There's gravity for you. I hope that helped. I hope that made some kind of sense. For another really good discussion on that, have a look at the Vsauce video. The Vsauce video on it, I will link it underneath this video so that you get some idea of how he chose to cover that particular subject matter. Okay, so the distance up or down the cone towards the apex or towards its base represents a vector distance away from the surface, or the vector distance between the surfaces of two bodies, which are therefore attracted to each other in space because of the geodesic line. What causes this phenomena to occur? Well, it is the observable, demonstrable, predictable, and observed in reality difference between the rate of time flowing past the given instant that we all agree is right now, depending on your distance away from a large amount of mass. In other words, mass causes time to slow down. Interesting. Lack of mass means that time flows more quickly. So basically a world line moving through space-time has a certain amount of gumption, if you like, a certain amount of impetus, and it moves through space and time. But the more it moves through time, the less it moves through space, and the more it moves through space, the less it's moving through time. Interesting stuff. So there you go. There's a little play with cones. There's a little bit about geodesics, what they are, how they work. Also, there is a pretty parsimonious explanation of gravity. It's a two-dimensional representation of a three-dimensional thing, a four-dimensional thing. Goodness, get that right. That's what it is. That's why it works. Join me next time where I will cover something related, but different. Any questions? Let me know. Please do comment under here to let me know what it is that was good, bad, or indifferent about this explanation. What did you understand? What did you not understand? How could I improve this explanation of the very, very real phenomena of gravity, which is both a force as defined and measured and in effect as observed. Predictably. Good. Okay, have a great day. Don't do anything I would. Trust me on that.